All right. I think it's time for me to get started. That means it's time for you all to sit down and shut up. How's everyone doing today? Was lunch good? I didn't eat any lunch because I was screwing off. Not nerves or anything. I was just chatting with people. Welcome to my talk, Understanding Probabilistic Data Structures with 112,092 UFO sightings. I apologize in advance if I'm a little hoarse. It's possible that I drank too much last night. Actually, I've just been nursing this cold for like 6 weeks, so I thought I'd come to Norway and share it with you all. So, my name is Royse. I'm a developer advocate at Redis. I like to say that there are 3 things on this slide that matter. One of them matters to you, one of them matters to me, and one of them matters to my boss. What my boss wants you to know is that Redis is more than just a cache. It can be a database. It's got a lot of, it's more than get and set. It stores more than strings. It does a lot of stuff. We're going to talk a little bit about some of the stuff that it does today. There's some probabilistic data structures that are available in Redis. We're mostly going to talk about probabilistic data structures, and then I'll talk a little bit about how you can use them in Redis if you don't want to roll your own. But we're going to go down into the details and how these things work. So that's the thing that matters to my boss. The thing that matters to me is all these social links here. I judge my value as a human being based on, I can't see the monitor. It's over here. Yeah, no, this is my most, no, yeah. Is that Twitter user right there. So if you don't follow me on Twitter and you're still willing to use Twitter, then give me a follow, please. And if you're not willing to use Twitter, I'm on Blue Sky as well, so I'm guy.dev there. And the thing on this slide that matters to you is that GitHub URL right there. So all of my code, my slides, slightly dated version, I need to update that. And all these examples that I'm going to show you today, they're all out there on GitHub. You can take a look at those on your own. In addition to a demo at the end that's on there, I also have implemented several of these probabilistic data structures I'm going to talk about in various programming languages, some in Java, some in JavaScript, some in C#. So pick your poison. I don't think I did any of them in Python, but does anyone care? So anyhow, so that's me. And I just want to point out that I did get guy.dev as a domain name. So there's that. It only cost me $180 a year US, but totally worth it. So 112,092. So this is an oddly specific number, but it's also a surprisingly large number. This is the number of UFO sightings reported in the National UFO Research Center, the NUFORC, that has been logging UFO sightings in the United States since about 1950 to present. So 112,092 UFO sightings. It's a ton of data. And this data is kind of fun and interesting because it's got a lot of UFO sightings, and some of them are like, and some of them, that person's on drugs. But I have this data, and here's what it looks like, thanks to a wonderful man by the name of Timothy Renner. And I always give him credit for this because I've gotten so much value out of his work. He likes to screen scrape weird data and then do data science with it. And so he went to the NUFORC's website, screen scraped all their UFO sightings, and built a massive CSV file, which is 112,093 lines long, because there's a header. And then he used it to do all kinds of analysis. He also screen scraped the Bigfoot Field Researcher Organization's website and got 4,092, what is it, 4,092? It was like 4,000 and some odd Bigfoot sightings. And did statistical and machine learning type stuff on those as well. The UFO sightings are fun because he did a couple of simple analyses. He did a histogram of the day of the year that UFO sightings are most likely to occur in. Remember, this is the United States that this is happening in. Any guess what day of the year is the most common one for UFO sightings in the United States? The 4th of July. That's right. I always just imagine, I know it's right, it's funny, right? I always just imagine like this father and son sitting down to watch fireworks. And the son saying, "Dad, is that a firework?" It's like, "No, son, that's a UFO." He also did an analysis to determine where the UFO sightings tend to occur. It turns out like 80% of them happen within 100 kilometers of a US airbase. Shocking. He did similar things with Bigfoot where he would look at the Bigfoot data and would do clustering algorithms to figure out where they tend to be grouped, and ultimately found out that you can find Bigfoot in the woods. So, and here I thought he was my father. But this is the data that's in, this is an example of the data that's in there. Here we've got a summary of that UFO sighting. This is well, it's a summary. It's exactly what you'd think it would be. Here we got 3 saucer-shaped ships, very easy to say. High in the sky, metallic but no shine, rather dull gray. They hovered overhead in a V formation. Sounds like a UFO to me. This happened in Salem, Oregon, because we've got the city and state that happened in. We've got a date time. Sometimes these are approximate. Sometimes they're a little more precise. These are just eyewitness accounts, so it's going to be like, oh, it was, no one's checking their watch, right? It's just like, oh, it was this night, and this one happened on September the 15th of 1950 at about 2 o'clock in the afternoon. We've got the shape of these UFO sightings. Disk is a shape. There are other things that are very unshape-like words that are used to describe shapes of UFO sightings, like object and light. The duration in human terms, so this is like 15 minutes or a couple of hours or that sort of thing. It's descriptive. It's not like a numeric value. The link back on the New Fork site for that sighting, the full text of that UFO sighting, that UFO encounter. We'll do some analysis on that later at the end of the talk. And then the latitude and longitude of the city where this happened. So this could be fun data. We could do lots of fun stuff with this. We're going to do statistical analysis at the end of the words that are used in UFO sightings, which is to say we're going to count them. And I'm going to demonstrate what probabilistic data structures are with some of this data. So this is the big question. What is a probabilistic data structure? Now, well, actually, let's do a show of hands. How many here have heard of probabilistic data structures? Okay, a few of you. Technically, it should be all of you because I just used the phrase. But we'll go with this. How many have actually used them in a production environment? I see like 2 hands. So if you don't know what a probabilistic data structure is, don't feel bad. Most of us don't. That's why you're here, right? I did a survey on Twitter when I was putting this talk together a couple of years ago. And fully 60%, like 3 out of 5, had never heard of them. And 1 out of 5 had heard the term, but they didn't know what it was. And the other 1/5 of the people had either knew what they were or had actually used them. So you're in good company. Nobody knows what these things are. So that's why we're here. But in order to explain what a probabilistic data structure is, I think it's best to talk about its evil twin, the deterministic data structure. The deterministic data structure is, well, it's the data structures you're already using. It's the ones you use every day here. I've got like lists, sets, arrays, graphs, tuples, stacks, trees, tables, queues, right? These are the hash tables that you use, or well, I'm guessing most of the folks here are probably .NET, right? That'd be fair to say? NDC is a little .NET heavy. So these would be the dictionaries that you're using in C#. If you're a Java person, these would be the hash maps. But these are like the dictionaries and the lists and the sets. These are the data structures we use all the time. And the reason they're called deterministic data structures is because they do what you tell them to. Like if I shove a bunch of data into a hash map, into a dictionary, I expect to get it all back out. And it doesn't change its behavior based on the order that I shove it in. It stores it reliably, deterministically, and I get it back. And so that's a deterministic data structure. And I'm going to dive into one deterministic data structure in particular, and we're going to talk about hash tables and how hash tables work. Now, a lot of you probably took computer science, and you took a data structures class, and so this might be review. But there's a lot of people that didn't have a traditional background, and so I want to cover this for those as well. And there's probably a lot of you that's like, well, I crammed the information about how a hash table works into my brain so that I could pass a test, and then I haven't used it in 20 years, which is me. And so, just for those who aren't familiar, a hash table is your dictionary, right? You got the key value pairs. I want to shove like the city, it's Salem. And so I can pass that string into that hash table and get that key back, get that value back out. It's kind of like a key value store. And the reason that they're called hash tables is because we use hashing functions on the keys when we're inserting things into the hash table. So a hashing function can be thought of as, well, it's a function that does a deterministic thing. If you give it some data and you give it a seed, it will generate a numeric value out of that data. And that data could be a gigabyte, or it could be a byte. All right, here I've got the UTF-8, if I can point to my screen again here, those right there. That's the UTF-8 strings, or the ASCII strings, bytes that make up the word Scully from the X-Files. And so if we shove Scully into the hashing function with a random seed number, and we use those same values both times, we will get out a numeric value that's like, say, a 32-bit integer or a 64-bit integer. And it's worth noting, I'm almost positive all of you have heard of hashing functions before, but it's worth noting that when you're building a hash table, you're not going to use something like SHA, right? You use SHA-256 for your hashing functions for your table, it's going to be slow, because those are cryptographic hashes. Those are made to be secure, so that if you make a small change to your data, you get a random change to your output number. Whereas the type of hashing functions you would use for a hash table, you don't care about small changes of the data making big or small changes to your output number. It's okay if they're close, as long as they're smoothly distributed. Because performance matters, but you don't have to worry about anyone reverse engineering your keys, right? You know, if you're hashing your password, then that matters a lot. But if you're hashing the word state so that you can access it later, it doesn't matter. So we're using simpler hashing functions. In my examples, I use murmur hash because there's a library for it, but you can even write your own. So hashing functions take blobs of data and turn them into numbers. A hash table then uses this concept, and our hash table here is this bit on the right. It's an array. It's just a fixed length array, and in that array, this particular implementation is using linked lists. There are other choices, other ways to do this, but this is a really simple one. And so what we do is we have an array of linked lists, and they're all empty starting out. And if I want to add the city of Salem to my hash table, I take the key, city, I run it through a hashing function, and I get a number. And then I modulus that number with the size of the array of linked lists. And that gives me an index. And then I can go straight to that index, and I can say, add this value to the linked list. Or if it's in the linked list already, replace it. And so here we do city, we get ultimately calculate a 1, and we put city Salem in there. And then when we go to add something else, say the state, we go through that same process and we get a different index. And so we're building up this array of linked lists with all the values. Now what can happen here, and this is why we use a linked list, is that we've only got 10 items in our little array here, so we're going to get a collision. And so when we go to add the shape of a UFO to this hash table, we get a 1 again. And so rather than just blow up or have problems, we add another thing to the linked list. And so we grow these linked lists over time. If the linked lists start getting too long, we'll expand our array and we'll rehash everything and reallocate everything. When we go to read from these hash tables, then we just follow the opposite pattern. We take the word of city, we get the index, we look in the index, we walk the linked list until we find the word city. If we don't find it, then we return not found. If we do find it, then we return the value. So that's like hash tables in what, 3 minutes? So just a little refresher. So, and I bring this up because the principles in a hash table, this hashing of keys or values and turning them into indices, and then storing things based on that index, is a common pattern in how a lot of probabilistic data structures work. So there's a purpose to this refresher. So when we pick our deterministic data structures, one thing we'll often look at is we'll look at the time complexity of our operations and the space complexity of our operations. And we'll make choices based on which one to use based on that. So we might pick an array because it has a time complexity that's very fast. Accessing an element in the array is O of 1. Constant time, doesn't matter. Conversely, we might say, no, we don't want to use an array because that wastes space. There's a bunch of empty values in there. If we've got an array of integers, I've got integers that are unallocated, that are just sitting there. It's wasting space. So I might want to choose a linked list instead because the linked list is exactly as big as it needs to be. And so it's got better space complexity. But to access things in the linked list, you have to walk it. And so it's got worse time complexity. So basically, arrays are fast, but waste space. A linked list is compact, but is slow. And so you make these trade-offs when you're writing your software. Now, most of us on our day-to-day, we just like, just use an array and it'll be fine. Or a linked list and it'll be fine. Or I'll use a hash table and it'll be fine. And so And a lot of times we're not really opposing the time and space complexity. We're not making that specific comparison in our brain. We're often looking at the capabilities of that thing. So we'll choose a hash table versus a list, because the hash table, because we want to store things by keys. And we'll choose a list because we have a list of things. And so we will look at them not necessarily based on their time and space, but also based on their capability. And one of the capabilities that you can trade off on besides time and space, and another capability you can look at, is accuracy. Accuracy complexity isn't a real word, but that's what I titled my slide. But the idea here is that you can make a probabilistic data structure. You make a data structure that's probabilistic, that will lie to you. And so it'd be super fast, maybe by orders of magnitude. It'll be super small by orders of magnitude. But 2% of the time, it'll give you a false positive. And you're like, well, I don't want my data structures to do that, right? It's like, no, it must always tell me the truth under all circumstances. Well, does it? Is that actually necessary? Because when you start scaling things up, it sometimes doesn't matter. Say you're a really large online video provider, that rhymes with tube. And you need to count unique views of a video, unique user views. Does it matter if the total views is 1 million or 1,000,007? Is that really that important? Is that important enough that you would store all 1,000,007 users in a table for that particular video or in some sort of data structure? Probably not. Probabilistic data structures solve this problem where it's off by a little bit, but it's close enough. And this isn't actually that foreign of a concept. Here we've got a wonderful picture of the Devil's Tower, which I think's in Wyoming, but it's in the Badlands. I just can't remember if it's in Wyoming or North Dakota or South Dakota. It's definitely up there somewhere. But anyhow, if you've seen Close Encounters of the Third Kind, then you know why I suddenly want mashed potatoes. That's a joke for everyone over 50. So this was featured, this mountain was featured, it's called the Devil's Tower. It was featured in the movie Close Encounters of the Third Kind. And this picture I have of it here is a JPEG. Obviously, right? And you can tell because if you look at that pixel right there, see it? Yeah, it's the wrong shade of blue. Because it's a JPEG and the compression is lossy. JPEGs in a way are probabilistic. You lose some of your data, but it's good enough. And so that's the same idea with a probabilistic data structure. That's the trade-off you're making. It's a little bit lossy, but it's good enough. Making sense so far? Good. I'm not crazy. A lot of probabilistic data structures can be thought of as sets of the Venn diagram variety, but that are unusual, that can only do a limited set of operations and sometimes lies to you. So like in a typical set, if you think of it like a set class in Java, you can add things to the set. You can remove things from the set. You can get the members of the set. You can do intersections and differences and unions and all that sort of stuff. You can test and say, is this thing in the set? You can ask for membership. You can get the cardinality of the set, which would be the number of items in it. Probabilistic data structures are often sets that only do some of these things. And so you might have a probabilistic data structure that tests for membership. I keep adding things to it, and then I can say, is this thing in the set? And it will say yes or no, or probably not and probably is, because it could be lying to you. You can create a probabilistic data structure that says how many things are in a set. So as you add unique items, like say the username example from unique views of a video, you can then get a count of those, how many unique things are in that set. You can do a frequency, which is starting to stretch the set analogy a little bit. But if you think of it in terms of I added the star 5 times to the set, and I added the square 4 times, and the circle 6 times, and the triangle 3 times, you can get a counting of things. So you can add these things to the set, and then say, well, what's the frequency of this in the set? How many times was this added? You can think of this maybe as a sorted set with a numeric value associated with it. And there are data structures that are optimized for this. There's also a data structure, the last one we'll talk about, around ranking, where it's sort of like counting, but instead of counting, it just keeps the relative order. So every single time I add something to it, it bumps the order around, but I can't get reliable counts out of it. But the relative frequency to each other is consistent. And so I can find out that there are more circles than there are stars, than there are squares, than there are triangles. And so these are the sorts of things probabilistic data structures can do. You can also do a similarity on some of these sets with some of these data structures, where you can measure how similar one set that is probabilistic is to another. We'll get into that when we talk about min-hash. There's a lot of choices out there, and I just grabbed a few off the internet here. I haven't looked at all of these in detail. Some of them I haven't looked in. I kind of know how they work, but I don't have a talk ready, and so it's not like in my brain. The ones we're going to talk about today are Bloom filters, heavy keepers, and min-hash. Of these, if you see the little dagger thing there, the little like cross, that means that it's part of Redis stack. And if it's got just a little, the hyperlog log's the only one that's got the double dagger, that comes with vanilla Redis. And so some of these are available in Redis as data structures you can just use, and you don't really have to know how they work, but it helps to know how they work, because then when they do weird things, you can understand why they do weird things. And so I'm going to talk about the ones that are highlighted in blue. There's several other here. They're different varieties. And I mentioned Redis stack, and so we're going to slide into the one slide that's an advertisement for Redis here. So Redis stack is, honestly, it's just Redis. It's Redis with a bunch of extensions to give it new data types and new commands, such as probabilistic data structures, or graph databases, or a time series, JSON objects, that kind of stuff. So we've got one for JSON search, graph, time series, and Bloom, which is for the probabilistic data structures. And so this is the version of Redis I'm running for all my demos that we'll see later. It's an easy way to get it up and running. It's just honestly, I always run it in Docker, get it up and running. It's quick and easy. And so it's how I run Redis all the time. There's information on how to get it. You can also just install it on your machine, compile it even if you want to, if that's how you want to live your life. So let's talk about some of these data structures in detail. First and foremost, we're going to talk about the Bloom filter. And Bloom filter is nice because it builds on some of the ideas in the hash table. It's actually a little bit simpler. And a Bloom filter is a set that you can add things to, and you can test for membership. And that's it. That's all it does. All of the operations are O of 1. So adding to the set, constant time. Saying, is something in the set? Constant time. In fact, it's practically the exact same code. Bloom filters will respond with no, this thing is not in the set, if you ask it, or probably yes. And so you can get false positives. It'll say probably back to you. So no or probably. They are of a fixed size, so when you create a Bloom filter, that's the size it is. It can't get any bigger. You can't change it after the fact. So it's locked in time. So when you create one, make sure you create it large enough for how much data you think you're going to be putting in that Bloom filter. But they are stupid, stupid fast. Here's how they work. So you've got, for a Bloom filter, you've got some hashing functions. Excuse me. And those hashing functions have, of course, numeric seeds so that they spit out different values. And you've got a bit array that's of a fixed width. And so this is literally, I actually implemented this in JavaScript, and I used a Boolean array, which is like stupidly inefficient. If you were doing this in C, you would literally just have a block of memory, and you'd be using bit shifting and stuff. But conceptually, you have a bit array of just all zeros. And so it starts out, everything's empty. There's all zeros in it. And you can add things to it. So what we're going to build here on these slides is a little thing to say, have I seen this UFO sighting before? And so you can shove the title of the UFO sighting into it, and then you can then ask it, have you seen this before? And it'll say no or probably. And so the first one we're going to add is my favorite UFO sighting out of the set that I've read so far, which is entitled Megatron in the Bushes. And the story is actually really funny. So these guys are driving down, I think in New Mexico, down a desert highway late at night. And they feel an urge, an important biological urge. And so they pull over and they find a bush to take care of this necessary bodily function. And as they're going to the bush, one of the guys hears coming from the bush, a sound that sounded like Megatron transforming. Not from the movie, but like from the 80s cartoon, right? That I'm proud of my imitation of Megatron. And so they freak out. It's like, because bushes aren't supposed to make that sound, right? And so they hop in their car and they take off down the highway. And then this glow comes up from behind the mountain and chases them for like 50 miles down the road. And I'm sure they weren't high at all. Great story. Sounds true to me. So when we take this string about this wonderful little story, we run it through these hashing functions, just like we did for the hash table. And we'll get numbers, like a 32-bit integer maybe. And then we will modulus these with the width of our Bloom filter, which is just 10 bits. We have a very small one. And this will give us an index. But instead of adding things to a linked list or anything like that, we just set the bits to high. So Megatron of the bushes turns into a bunch of indices, which turns into 1, 1, and 1 in those positions. When we go to read it, we do exactly the same thing. We take Megatron in the bushes, we run it through the hashing functions, we get indices, and then we look and say, are they all 1? If all of them are set high, then the answer is probably. If any of them are 0, we know that it couldn't have been added because nothing was ever put in there that would set all of them to high. If it had been added before, they would all be set to high. They'd all be set to 1. So this is how we add a thing to a Bloom filter. We can add another thing to the Bloom filter. Here's another wonderful UFO sighting. This one is in my hometown of Columbus, Ohio, and this is exactly how it appears in the text. I seen a UFO when I was about 13 years old. The bad grammar is correct. The all uppercase is correct. This is exactly how it shows up in the CSV file. And so I'm preserving the original. And we run this through that same process, and we get different indices. But you'll notice that one of them, the one that I've got circled right there, that one was one that I had before. That was part of Megatron in the bushes. But we set the other ones to high, and it's fine. And if we go and read Megatron from the bushes, we get all 1s. And if we go and read I seen a UFO when I was about 13 years old, we get all 1s. And so these are both probably in the Bloom filter. And this is why we don't just have like one hashing function. If we had one hashing function and we set it to set a Boolean, then another one could come in and clobber it, and then we wouldn't know. And so by increasing the number of hashing functions that we have, we get some redundancy so that the overlap, the hash collisions, don't make it invalid. But then, because we have more hashing functions, we need more bits. And so there's a formula for figuring this out. I've got it on a slide. I'm not going to talk about how it works because there's a web calculator you can use instead. But what can happen, of course, is something probabilistic. Here we've got investigators from the Bigfoot Field Researchers Organization observing a glowing green-blue sphere. And all of these indices that are generated are all collisions. And so if I add this to the Bloom filter, the state of the Bloom filter doesn't change, but I've added it. And then if I go and read it and say, have I seen this? It'd say, yes, you've seen this. This has been added to the Bloom filter because we had added it. But if I hadn't added it and I asked the question, has this been added to the Bloom filter? It would say, yeah, probably, even though it hadn't been added to the Bloom filter. This is why it's probabilistic, because the order you add things in kind of matters. And you can also see why, if you extrapolate this out a few more times, why knowing how many things you want to put in your Bloom filter really, really matters. Because what will eventually happen is everything will be 1. You'll fill it up. And then it's like an American. It just always says yes. And you know, it's like false positives for everyone. You get a false positive, and you get a false positive. So yeah, that's in a nutshell how a Bloom filter works. Here's the formulas that I threatened to show you. They're actually not that bad. You can solve for k and then solve for p and guess for a number you want. But you just use the online calculator. And of course, you can use these from Redis. Redis has a command. If you have Redis stack with Bloom in it, you can call bf reserve, and you give it a key name for Redis, and you give it an error rate that is acceptable. Here I've selected 0.5%, and you give it a capacity. So I'm expecting to have 100 things, and I'm willing to accept a 99.5% accuracy rate. And so this will create one for me. And then if I want to use it, I call BF add. I give it the key name and then the word that I want to add. And there's a multiple version of it called MAD, which is very attic. Small detail here that I think is kind of interesting is that you notice here, come on, I'm returning 1, 1, and then down here it returns 0 and 1. So that 0 or 1 is telling you whether the bloom filter changed or not. So you can actually just add something to it and know whether it was there or not. So you can use this for deduplication. The 0 there says, I've added light already, so the bloom filter didn't change when you added light. You can get that 0 back, though, like in the case of the BFRO seeing a green-blue sphere, that would return a 0 as well, because the bloom filter didn't change. So it's still probabilistic. It's just a little bit of extra data. And then the only other command that's really there is bf.exists. You give it the key name, you give it the value, and it'll tell you whether it's in there or not. And it'll say yes, it'll say no, or probably. And there is a multiple version of this as well. I always like, one of my running jokes at work is I like to pronounce Redis commands like they're words. Like, so we've got a set data structure, and set add is sadd or sad. You know, it's the loneliest of all Redis commands. And like there's a increment by in a hash. To increment a numeric value in a hash, it's hinker by, and so I call it hinkerby. So this one is mexists, which always sounds like Mexican extremists to me or something like that. So, but anyhow, yeah. So here you just, it returns the same thing that you got when you added it. So that's bloom filters. So let's talk about one that's not in Redis. Let's talk about minhash. So we got, what, about half an hour still? Yeah, we're good on time. We got plenty of time. So minhash is, I believe it was created by Google to determine whether a page had changed enough to justify reindexing it back in the early days, I think in the late 90s, early 2000s. But I could be totally wrong on that history. Someone from Google's watching this right now. They're like, he's so wrong, you know. Okay. But so what they do is they determine set similarity between documents. So let's say you all wrote term papers, and I wanted to see who cheated. I could use this to compare all of the term papers to each other and find how similar they were, and get an index of, if they're more similar, you might have cheated. Who here cheated? Someone's going to raise their hand and be a smartass. I know it. So you can use a minhash to do this in a probabilistic fashion. So before we talk about that, though, we need to talk about how we can compare sets. So what is set similarity? Well, it's just how similar two sets are. Here's a simple example. We've got Scalder and Molly here, face swapped. And these are the states of the United States in which they've seen UFOs. And so Scalder has seen them in California, Nevada, Oregon, and Wyoming, and New Mexico and Ohio. Molly has seen them in Florida, Kansas, South Carolina, West by God, Virginia, New Mexico, and Ohio. This looks real to me because New Mexico, Area 51, Ohio has Hangar 18, where the bodies from Area 51 went in Dayton, Ohio. So probably, it looks legit. But to calculate the Jacquard similarity of these two sets, what you do is you take the cardinality of the intersection, that's how many items are in the intersection, that's Mexico and Ohio, so there's 2, and you divide it by the number of items in the union of the two sets, which is 10. It's all of the ones that are on the page here. And you divide them, and then you get a ratio, and so these are 20% similar. It's that simple. Not a complicated calculation. And so you could do this to documents, sort of. So if you took all the words in a document and all the words in your document, I'm going to point you to, if I took all the words in your term paper and all the words in your term paper, put them in sets and got the intersection of those, there'd be a lot of words in common because they'd both be in, well, I'm going to guess Norwegian. They might have been in English, depends on where you went to school. But they're probably all in the same language. And so all this is really telling us, if they're highly similar, is it's English or it's Norwegian. And so that doesn't work well, you know, on the face of it. So how can we turn a document into a set to do a Jacquard similarity comparison? Well, you use a process called shingling. Shingling is taking trigrams from the document and adding those to the set. So we take the first trigram. We notice 2. And then we take another one that's just shift over by 1. Notice 2R. So they overlay on top of each other like shingles on a roof. So it's not really a very clever name. And then we build up a set with all these values in it. And so now this text here, we notice to our left, further off into the mountains, a bright glow. This is the Megatron in the bushes story. And this builds up a little set, and then we can do a comparison, right? So now we can take Scalder's report and Molly's report and compare these trigrams, sets of trigrams, and get an intersection and a union and get a better Jacquard similarity score. And here we see that they're, about 2/3 the same. And so Skinner is happy that Scalder and Molly have seen a similar enough thing. Their reports are similar enough. But there's a problem with this. Any guess as to what it is? If I'm going to take everyone's papers here and turn them into strings of sets of strings and then compare each one, that's going to take a while because I'm doing a bunch of string comparison, and I've got, it's a fully connected graph. Every single paper has got to be compared to every single paper. Not super practical. And so there's a way to calculate a min hash off of this set, this shingled set. And so the way it works is you walk through the entire set, you run it through a hashing function with its seed, just like we did in the previous example. And then we get new numbers for each entry in this hash. So in this example here, 325 corresponds to we notice 2, 489 is to notice 2R, and then all the way to 312 corresponds to the mountains A. And then we take the smallest number out of that set. And we do it again, and we do it again. We probably in practice do it more than 3 times, but 3 fits on the screen. And then we get a set of numbers that we could do a Jacquard similarity comparison against instead. So we do it here, do the same thing for Molly. We get different numbers, but some of them are the same. And we can take these sets of numbers and do the Jacquard similarity on those sets of numbers instead. And then here we get a less granular number, mostly because I use 3 hashing functions. So it's just not going to be as precise of a number. But this is a lot more efficient, because now we're comparing everyone's numbers against everyone's numbers, much faster operation than comparing a bunch of strings. And I kind of mentioned, why is this less granular? It's because I used fewer hashes. So that's min hash. Min hash, you can see how this would be really useful. You can calculate that min hash and hold on to it. And then when you come to that web page again, you could calculate the min hash, and you don't have to store the previous page, you just have to store the previous min hash, and then you can compare them and see if it's worth indexing again. So it can be very powerful. Let's look at the last and most complicated one, which is top K. Top K ranks items. And specifically, well, it's really heavy keeper is the thing we're going to talk about. Top K is a combination of a heavy keeper and a min heap. I'm not going to talk about how min heaps work. We'll just take them on faith that they work the way they do. And then I'm going to talk about the heavy keeper. But the idea here is that I want that ranking without necessarily having accurate counts. And so I want to find the top 10 most common IP addresses that hit my site. Or I want to get trending topics. And the cool thing with Heavy Keeper is that it's erosive. So as I add things to Heavy Keeper, it hangs on to them. And I keep adding things. But occasionally adding something will create a conflict inside of the Heavy Keeper structure that results in the counts being dropped for values that are in there. And so it keeps track of, it sort of measures flow. So as things come in, as IP addresses hit my server, I add them to this top K, they will keep building up, and then when it stops happening, other things will come in and chip away at its count until it's removed from the Heavy Keeper. And so it does this probabilistically, of course. They're actually kind of a complicated structure, but we're going to dive into it anyhow. Again, like I mentioned, they're good for things like trending topics or network traffic analysis. If you've got, hey, what are the IPs that are hitting me most? I bet you they're hacking me, or they're trying to do some sort of DDoS or something like that. A Heavy Keeper, again, has a bunch of hashing functions with associated seeds. And then associated with each hashing function is an array of buckets. And then you can choose when you create this how wide it should be, how wide these arrays should be. And then you create these. You can choose how many hashing functions you want. So you can basically choose a height and a width. And each bucket has a place for a hash value, and it has a counter. A brand new heavy keeper has nulls for all the hash values, and has a count of 0. And so here's how it works. Let's add a value to our heavy keeper. Let's add the word object. We're going to add UFO shapes. Object's a shape, technically. And so what we do is we take that object, we run it through our hashing functions, we get hash values out, which this is a pattern we've seen a couple times now, and then we modulus that with the width of our heavy keeper, and we get an index. And what we do is we ask ourselves at that index, we'll look in that index and say, is this index in use? Is there a value in the hash? If there isn't, which is the case here, we'll claim it. And so in this case, this heavy keeper is empty, and so each of these values just gets populated, and we put our hash value in the hash position, and we put our count, and we take the count from 0 to 1. If we add object a second time, it's going to go through, it's going to calculate these hash values again, it's going to get an index, it's going to look in that index, and it's going to say, this index is taken. And it's going to say, well, is it mine? Is this 5062 here match the value in here? Yes, it does. So we increment the count. And as we add object over and over again, the count will just keep getting bigger and bigger. And when we go to query this then, when we go to read it, we can ask the heavy keeper, say, how many times has object been added to you? Well, then we just do that same reverse process where we take the object, we get the hash, we modulus it, we get an index, and we go in there and we look at the index, the bucket of that index, and say, is this our hash? Yeah? Okay, well, there's the count. We do that for all of them, and we take the largest count. In our case, these are all 2s, so we get 2. So when we query this, we get 2 things. So kind of boring. This sounds like counting the hard way right now, right? It's like counting with extra steps. But it gets interesting when you start adding other things. So another popular UFO shape is light. And with light, we do this calculation, and in the first row, we find an unclaimed bucket, and so we claim it. And in the second row, we find an unclaimed bucket, and we claim it. But in the third row, we go there and we say, well, there's something in this bucket, and it's not us. It's not ours. What do we do? And this is where it gets interesting. So there is a possibility that the count will be reduced by 1. And so because there's a conflict, we'll basically roll the dice and determine whether we're going to erode that value, reduce that 2 to a 1. And if we knock it out, if we knock it till it's empty, something else can come in there and take its place. And this calculation uses this fairly simple math, where the probability of decay, the probability of erosion, of reducing that count by 1, is equal to a magic rate value that we put in when we create the heavy keeper, which is greater than 1, but very close to 1. I'm using 1.05. And then we take that number to the power of negative the count. So we've got 2 things in there. Our count is 2 that we're trying to see if it erodes or not. Take it to negative 2. And so if we've got a small number in there, our odds of erosion are high. 1.05 to the power of negative 2 is 0.907. So it's 98.7% likely that it'll erode. If I had 1 million items in there, or 1,000 items, you get a much smaller number, and the odds of it eroding are much lower. And so this allows things that are, once they get in there, if you get a high count, it's unlikely that they'll erode. They will erode occasionally, though. If you get like a 1% chance of erosion, but things are just coming in, they're conflicting with it all the time, you know, it's going to come up, you know, you're going to roll natural 1 on that 20-sided die eventually, right? It's going to happen. And so it erodes it over time. This is why it works so well for trending topics, because those things will be, the counts will erode. So in our case, we're going to say that we roll the dice, probably this is going to erode, this is going to decay. And so that position there is still claimed by the hash value of 1442, but now has a count of 1. It's been decreased. So now, after decay has occurred, we can query the word light and we get 2 hits. The third row, we get the mod index, we go and look, but it's not ours, so we don't count it. So we look at the other 2 that are ours, and we see there's 2 ones, and we say, well, there's a light has been added to the heavy keeper once. And when we go to query object, we get 2, 2, and 1 for our numeric values, and we take the biggest of all of those, the largest, and we get value 2. And so the count has been preserved. And then, but as this scales up, these things get torn away, and they can disappear entirely. What this means is that heavy keepers are actually terrible at counting. Because they're erosive in nature, they tend to always underrepresent the count. And so they're not actually good for counting. It's not the point of a heavy keeper. The heavy keeper's point is just to keep track of, hold on to the things that are heavy and let the small things just be eroded away. And what we do is, alongside this heavy keeper, we have a min heap. And so every single time we add something to the heavy keeper, we'll look at the count that we have for that thing we just added, and we'll say, how does this compare to the min heap? And we'll add it to the min heap and sort it, and then it'll chop off all the things at the bottom. And so we'll just keep the top 5 there all the time. And so then things can be added and removed to that min heap. And so then when we use our top K structure and say, give me the top 5 most commonly used words in UFO sightings, we just interrogate the min heap, and it tells us. If we want to get the counts, we can go into the heavy keeper and go look. They're going to be inaccurate, but they will be relatively valuable. They'll show you the ranking. So that was a little dense, I know. To do it in Redis, you call topk.reserve, you give it a key name, you give it the number of things you want to keep track of. So this is like the top 3 UFO shapes. You give it a width of how wide you want those arrays to be, and you give it a depth, which is how many hashing functions you want to use, and you give it a decay value, which is the reciprocal of that 1.05 that I showed you in my example. To add to a top K, you just call topk.add, give it a key name, give it a thing or multiple things. So here we've added disk 3 times, we've added teardrop twice, we've added light once. And then if we want to say, is this thing in the top K, we can call topk.query, give it a shape, and it'll say yes or no. Or we can say, give me the count of a particular thing, and it will go into the heavy keeper and give you the count. Or we can say give me the top K items in order, and it will go to the min heap and just spit them out. And so this is a complicated data structure, but it's actually very easy to use from Redis. So I have used this data structure to do this statistical analysis on the shapes and the words used in the UFO sightings. So let's slide over to a demo. So now I feel like I have to hunch over because this podium is slightly low. Here we go. Everyone see that? There we go. So what I've done is, and I'm not going to go into the code a ton here, but what I've done is I've got this CSV file. Where's that here? There it is. This is all the UFO sightings. 112,102. Wait a minute, that's wrong. If I go to the top here. What's that? Yeah. I'm sure it was a great joke. And Megatron in the bushes in here, but there's a ton of these. It's just a CSV file, very easy to work with. And so what I do with the CSV file is I've got 2 Python scripts. One is going to parse the CSV file using pandas, and then I run it through NLTK and a bunch of other Python stuff. It kind of doesn't matter, really. Ultimately, I'm using Redis to do the top K stuff, and so I parse this out. I run it through NLTK to get rid of like common words in English, so it's not like a, and the are the most common words used in UFO sightings. And I remove any numbers and stuff like that. And then I start adding them to 2 top K structures, one for the shapes and one for the words that are used in the sightings. So I'm just going to go ahead and run it. So we're going to go Python. I almost typed Python. Don't ever go there. Yes, it's a site. Build.py. So build.py is going to start kicking off here. Let's just go ahead and begin that. And so these are the sort of the normalized text that I'm being added, and we're adding this to a Bloom filter, or to a top K structure in Redis. So if I go over here to Redis, this is Redis Insight. It's a nice little GUI client for Redis. Click on that local one, refresh my keys. See, I've got a data structure for UFO words and one for UFO shapes. If I go down here and enter a command, I can do like topk dot list. Is that big enough? Can everyone read it, or do I need to embiggen it? Okay. I'm going to go with your silence and assume that's big enough. So if I go to topk.list words, oops, hang on. There we go. So those are the words it's picked so far. It's lights, object, light, sky, saw, like, one, see, moving, bright. And now you see as I run through this, they change over time. So I'm adding these things to these top K structures. I could do like a top K.count UFO words and light. And if it helped if I could type the word count. And there's 1,279 of them, probably. So I've got another little bit of code here, though, that is a little app that makes this look a little nicer. Oh, there we go. And we're going to run app.py. And so now I've got a little web server running. If I go to localhost port 6001, it goes out, and it's just basically querying. It's doing the commands that I just did, but just through a REST call periodically. A REST call. It's not really RESTful. It's just a call. And so you see that you see light, lights, the common words here. The UFO shapes are kind of fun. Light is the #1 shape, followed by circle, which is a shape. Triangle, which is a shape. I guess sphere is a shape. It's just 3-dimensional. Other is a shape. Unknown, disk, fireball. That's my favorite shape when I'm playing D&D. Oval and formation. It's a formation. That's a shape. So yeah. So this is going out there, and it paused there for a moment. I panicked. And then I heard my fan kick off on my computer. The Python scripts are doing quite a bit of compute. So, but yeah, so this is my fun little demo. Kind of worthless, kind of fun. Those are the best kind of demos, aren't they? So let's go ahead and get back to the slides here. Okay. No, come on. There we go. So it's just a little slide full of resources if you want to play around with this stuff yourself. There's a wonderful blog post from Bloom Filters by Example that had a great visualization that helped me think about how to visualize Bloom filters. We got a Bloom filter calculator, which I mentioned earlier. This is, if you want to decide what your value should be, you can use that. There's a tutorial on minhash, which was very, very useful in putting together this talk. And there's a white paper on HeavyKeeper, which I read so that you don't have to. We've got the UFO Sightings dataset put together by Tim Renner. If you want to go download this and play with it yourself. The National UFO Reporting Center is the source of those, the newfork.org. Real website, real organization. I don't know if it's real UFO sightings or not. Got a kind of a dated blog post at this point. I probably should take it out of the slide here on called Meet Top K, written by one of my coworkers, who actually was the person who implemented the Top K data structure in Redis stack. And then we've got, if you want to get Redis stack, there's a URL for it. And if you want to check out Redis Insight, which is the little GUI client I was using, it's actually, you can go there and download it, but it's also in the Microsoft Store and in the App Store for Apple. So you can just download it that way. And yeah, I work at Redis. We have a Discord server, so if you have questions and you want about Redis or anything, ping me on there. We got free classes, and we actually, my coworker Simon is putting together a class on probabilistic data structures right now, so we have one coming soon. And sign up for a free version on Redis Cloud. There's QR code for my slides, so you don't have to write any of this stuff down. So go ahead and scan that. It'll take you to the repo. This QR code will never give you up nor let you down. And I think I've got a little bit of time here, a little bit early, so if there are any questions, I can take a question or two. You may have to shout because I can't necessarily see if you're on this corner. So if anyone got any questions? You're like, no, I don't have any questions. This is like the densest damn talk that I've ever attended. So, okay, well, in that case, thank you very much. I'll be hanging out afterwards, so feel free to come up to me later.